Welcome to RSET online lectures on the subject CS309 Graph Theory and Combinatorics. It's a continuation of Semester 5 Module 2 Part 4. Here we discuss on Dirac's theorem. The theorem states that a sufficient condition for a simple graph G with n greater than or equal to 3 vertices have a Hamiltonian circuit is that the degree of every vertex in G be at least n by 2, where n is the number of vertices in G. Proof of this theorem was done by contradiction method. We assume that the theorem is false and derive at a contradiction. First, we assume that G is a simple non-Hamiltonian graph with n vertices satisfying the given conditions on the vertex degrees. Since it is non-Hamiltonian, we can add extra edges if necessary, and we assume that G becomes a Hamiltonian and simple. A Hamiltonian circuit means it is a connected graph defined as a closed walk that travels every vertex of G exactly once except the starting vertex at which the walk terminates. And since it is assumed that G is non-Hamiltonian, we add extra edges to become a Hamiltonian and simple graph. That is, the addition of further edges gives a Hamiltonian graph. But since G is non-Hamiltonian, the vertices V1 and Vn are not adjacent. And it is given that degree of Vi is greater than n by 2 for each I, then it follows that there must be some vertex Vi adjacent to V1 and some vertex Vi minus 1 is adjacent to Vn as shown in the figure. Now from the figure we get V1, V2, etc. Vi minus 1, then Vn, Vn minus 1, etc. Vi and back to V1, which gives a Hamiltonian cycle, which is the required contradiction. That means our assumption is wrong and hence the theorem. The summary, we define walk, open walk, closed walk, path, in which universal line and Hamiltonian path. In closed walk, we define two, that is circuit and Euler line. Then in circuit, we define Hamiltonian circuit, and in Euler line, arbitrarily traceable. Now we can define weighted graph. In a graph G, every edge EI is associated with a real number. That number is denoted as W of EI and it is called the weight of that edge. That number can be a distance in miles or time, etc. Such a graph is called a weighted graph, W of EI being the weight of the edge EI. And one application of that weighted graph is traveling salesman problem. In this problem, a traveling salesman wishes to visit several given cities precisely once and return to his starting point, covering the least possible total distance. In that case, we can consider a complete graph. And for example, if there are 5 cities A, B, C, D and E, the distance are given as weight in the edges. So what we want to find is that the Hamiltonian path with minimum distance. That means we are starting from a point and ending at the same point, visiting all the edges, all the vertices exactly once. From that, you have to find the shortest possible route. From in the figure, it is clear that the shortest possible route is A to B, B to D, D to E, E to C and C to A, and which gives a total distance of 26. And this is evaluated like this. Theoretically, in the problem, we can find n minus 1 factorial by 2 Hamiltonian circuits. And we find the n minus 1 factorial by 2 Hamiltonian circuits and its traveling distance. And calculating the traveling distance in each and then picking the shortest one. This is the problem. The problem can also be reformulated in terms of weighted graph. In this case, the requirement is to find a Hamiltonian circuit of least possible total weight in a weighted complete graph. The number can also be referred to times taken to travel between cities. That is, that weight can be considered as either time or distance. With this, we complete part 4. Thank you.